Hello everyone, we are going to take a look at predictive models in the next two modules. This one is going to look at linear regression, and next week we will look at logistic regression. And because this is such a big departure from what we've been doing, looking at descriptive statistics, correlation, t-test, and ANOVA, we're going to spend a little time with some of the information you need to know or will be useful for you to know in understanding predictive models. We're going to start with going right back to the basics. There are multiple branches. Has been traditionally said there's multiple branches of analytics. Descriptive is what we can learn about today from the data that we have. With just looking at the data, using the descriptive tools that we looked at earlier, we can learn about our data and what it's telling us. Discovery is what new information can we learn from our data, and that's kind of what data mining is about. It's about seeing what is in the data that may not immediately step out to us in the descriptive tools, but we can find good, useful information that is hidden. Predictive is part of that discovery process, but it's also set out as a separate branch because it's so important. And I think as we go through this presentation, you'll start to understand and see where predictive can really take us. And just as a side note, if you are doing the specialization or certificate in data analytics as part of your degree, there is an entire course dedicated to predictive analytics. It's called Applied Predictive Analytics, and that's IT 483, typically taken at the end of the sequence. So you'll come back to this and study it a lot more. In that class, though, we use Python to build predictive models. So it's an opportunity for me to teach you more about predictive models and for you to learn how to code in Python. And the last branch is prescriptive. What does our data tell us that we should do? By the way, predictive is what can our data tell us about what's likely to happen. And then prescriptive is what does our data tell us about what we should do. So far we spent a lot of time talking mostly about descriptive and discovery analytics, but now we're going to take a look at some predictive models. So we're going to build a predictive model. And what does that mean? So what that means is we are going to use old data to predict the future. There's no magic going on here. There's no mystery. All we're doing is looking at old data and saying, oh, this is what the relationship was between variables in our old data. We have a reason to believe that it's what the relationship is going to be in the future. And the way that we could use this is if we were to go back into the sales of a used car dealership. It's a great example because if you're trying to sell used cars, you don't always know the right way to price them out. And lots of times there's quite a bit of negotiation that happens before the car is actually sold. So if you were able to track certain features of your used cars that you've sold, along with the price, in your old data set, you could build a linear model that shows you that when a car fits these particular parameters, its sale price is Y. And when it fits other parameters, it has a different sale price. You can build that relationship between those old data parameters and then use that model, that resulting model that comes out of it, to price new cars when they come to your lot. So you can apply the model you create to more accurately priced cars. You don't want to overprice them or they won't sell. You don't want to underprice them or you're leaving money on the table. So it's a much better predictor when you can build a linear model like this. So we're going to build a linear model in this presentation, and it's going to be based on old data. It works best if we have a lot of old data. We get a much more accurate model. It works even better if the fields that we want are already related, which makes our model even stronger. So we have two types of variables when we're building a linear model. We have an independent variable or independent variables, because sometimes we have more than one. And those are the variables that help us predict what the outcome is going to be. Then we have the dependent variable, and that's the variable that we don't, once we have a model, it's the variable that we don't know. It's a variable that we want to predict. And that variable, once we build our model, that variable is going to be predicted based on the values of the independent variables. So the independent drives the dependent. And it makes sense because independent, of course, is independent. Dependent is dependent on the independent. So we will see how the dependent variable becomes the outcome of this process. It's the outcome of your model. So an example, and one that we'll look at in JASP, is the amount that you study, that's your independent variable, will directly affect or impact your exam score, which is your dependent variable. So independent variables predict dependent variables. And that's how we build our model. So what we're going to do is we're going to get an old data set. It's going to have the independent values and the dependent value. We're going to look at the relationship between the independent values and the dependent value. We'll calculate some values. Two of them are slope and intercept that define the relationship between our independent variable and our independent and our dependent variables. And we'll use that relationship on new data where we only know the independent variables. Okay? So let's use our used car sales as an example. We're going to go back into our database and we're going to pull up a history of the last, say, 3 years where we know that the year of the car, the size of the engine, and the number of doors are independent variables that impact the price of the car. We have that information, so we pull that information, right? Then we look at the relationship between those independent values and the dependent value. How are they related? When there's 4 doors and the year is less than 5 years old and there's other features, the price is set to be some value. So we look at each one of those instances and then we look at them in aggregate and we say, okay, under these conditions, we can basically predict what the price of the car should be based on what it has been in the past. But we'll build the model. We'll go through and we'll calculate some values, and we come up with 2 things that are really important, and we'll go into them in a lot more detail later on in this presentation, but it's the slope and the intercept. And that's what we use whenever we receive the information that are the independent variables. We apply the slope and the intercepts to those to calculate what the dependent variable will be. Then, once we have built that model, say we get a shipment next week of 100 used cars, we are going to apply the model to each one of those cars one by one to determine what we think the best price should be. And that's the way that we can create that model. Here's another example. Let's say, for example, we are a retailer and we keep track of our customers and their sales, some number of them, not all of them, using sort of a loyalty program. So we know on a good number of customers what they've spent all year long. So each year we're going to track for those customers all of their sales, all of the kind of financial sales that they made between January 1st and November 30th. And we want to know, is that a good way or good predictor for how much they're likely to spend at Christmas time? Because that can be a time when they spend quite a bit of money at our store. So if that turns out to be a really good connection, a really good way of being able to predict what their December sales will be, do we use that information to market to those that are likely to be big spenders? Can we send them sales flyers? Can we send them other information to incentivize them to purchase more at our store? How do we market to lower spenders? Maybe we send them sales that are the other way. We give them discounts and the like. Or do we bother to market to them at all, right? Depending on what our model tells us. So there are mathematical formulas that will help us with this, and that's what we're going to be doing with linear regression. A little bit of terminology. This is not hugely important, but you may come across these terms when you're doing data mining work. And it's supervised learning versus unsupervised learning. In supervised learning, we are basically creating a model on past data. So the supervision is really the past data. The past data defines the rules that will go into creating our model. And we might do this in a couple different ways, but the most common way is we would take our data, our past data, and we'd break it into 3 sets. The first 2 sets will be the biggest sets, and then the third set will be a smaller set. The first set is the training data, and that's the training data that we use to actually build the model. So we look at the relationships between our variables in the training data, and we build a model based on that. Then we may take a chunk of our data, and we will validate the data. So the training model builds it, but we don't want to use the training data we use to build the model, but we don't want to use that same data to validate the model. So we use similar data, maybe from the same data set, and we will go through and we will put in our input variables. We'll check our output variable, our dependent variable, against an actual value to see how far off it is. So we can get an idea of how accurate our model is. And then we might take a small chunk of our data that is maybe not from the same data set, most often not from the same data set, and we might test our model because there's this thing called overfit, where if we are really, really good and we build a really great model using our training data, and the training data and the validation data may become from the same data set, we may and so we validate it. It looks great when we validate it, but it's too tightly fit to that singular data set. And so when we put similar data into it, It doesn't work very well. So that's just kind of an aside an approach to supervised learning, but just probably, if anything, you remember from the slide, just remember that supervised is basically building a model on old data. Unsupervised learning does not do that. It doesn't use training or test data. We're going to get into some tools towards the end of the class. We're going to look at clustering and classification. Those do not use, well, classification does, but clustering does not use supervised learning. So back to the training data. All right, again, we're looking at what has happened in the past. And in our example for cars, we might go back 3 years of sales, although that's going to be a little kind of compromised by the fact that prices fluctuate. And so used cars cost more today than they did 3 years ago. So we may have to take that into account. But with our Christmas sales, we're going to look at what happened just this year. Now, again, there's been inflation this year, but in past years, it could be a pretty good indicator of what the relationship between the variables has been. So what has been the relationship between the variables in the past is what we want to know. How much data is this based on? We don't want huge amounts of data, but we also don't want a small amount of data where our model isn't going to be very reliable. So by understanding the relationship between one variable and another in past data sets, can we predict how similar data sets will behave in the future? So can we build a model that takes input variables and outputs predictions? And this is the example that we were talking about earlier, sales for the year and Christmas sales. So linear regression as a prediction method is probably the most simple, straightforward, and what we're going to talk about today is going to be single or simple linear regression. I've indicated that you can have multiple input variables, but the simplest models just have one input variable, so we'll make this easy. So what is the linear relationship, or what has it been, between two variables? And we typically refer to those in a linear model as the input variable being x and the output variable being y, or the predicted variable being y. So x is the input, output is y, it is the dependent. It's the one that changes when the input changes. Okay? But to what degree? In that next bullet, you'll see the linear regression equation. Y, which is the predicted value, is equal to the slope times x, the input value, plus the intercept. Now, we haven't seen slope and intercept yet, and that's coming up in a slide. But when we build a model, it can be as simple as this, but when we build a model, the statistical tool will give us both the slope and the intercept. It goes back and looks at the old data, determines what the relationship was in the old data, and calculates for you a slope and an intercept. That way, you already have the y and the x in your old data. You can validate your model, but in the future, you may not have y. You don't know the price of your used cars. So you're going to use the slope, the x value, which is whatever input you're looking at, whatever predictor you're looking at, plus the intercept to determine your predicted y. So what are slope and intercept? In the simplest terms, we'll take the intercept first. If you're looking at a graph and you start, your lower left-hand corner starts at 0, then on the horizontal axis you proceed to some values, on the vertical axis you proceed to some values, but the vertical value is 0. The intercept is where your line, your linear prediction line crosses the vertical axis. And this is not going to make any sense without a visual. But it's basically the 0 point. The slope is the amount that your line changes with every unit of increase or decrease. So we'll have to take a look at it. But it's very predictable, and it's very common, and it's very simple. And so that's why we call it linear, because it's always going to change in the same way. It's always going to change in a linear fashion. Here is a great way to look at this. I've got you a graph that we can use. Okay, so when we plot, this is scatter plot. These are basically different lengths of different flowers, or parts of flowers, petals and sepals. When we plot these, we'll get a scatter plot. And so each one of these represents a measure on both the horizontal axis and the vertical axis. And we see that our data are pretty related. They're pretty closely related because they follow kind of a positive sort of diagonal line. So when one goes up, the other one typically goes up. Okay? This would be a great data set for predicting one using the other. Now, when I said that the intercept, if we were to draw a horizontal line that was as close as possible to most of these data points, it would at some point cross a 0 point, which might be over here, because this is 2, 4, 6. If we keep going the other way, we're going to get to 0. That is the intercept value. Whatever that value is, where it crosses the 0 line, is going to be your intercept. It's your starting point. Okay? And then as we move each unit over, increasing the value on the horizontal axis, we are going to move some amount up, which gives us our diagonal line. And that becomes our slope. So we can see that there's a slope. Now, if something is very, very closely related, we might have a very nice diagonal slope. If something is not as closely related, or maybe one goes up much faster than the other, we might have a line that starts here at the beginning and goes much more sharply up. That's got a much more steep slope. Or we may have one the opposite direction that has a much less steep slope. But the slope and the intercept, again, the intercept is the starting point. It's where the line crosses 0. And the slope is how fast does it go up, okay? So in this particular case, we see a relationship. To me, is it strong enough? It sure looks like it's strong enough. That's a pretty good diagonal line that would cross through that. Is there enough data? A reasonable amount of data. And then we want to do something which is the regression line. Now, I've mentioned slope and intercept. What really determines slope and intercept is that regression line. And it's the diagonal line we would draw in this data. Now, we don't just randomly draw a diagonal line and think it looks good. There is a very mathematical process for predicting what, or for determining what that diagonal line should be. And the simplest way of explaining it is draw the line that is as close as possible to every data point. Okay? And you can simply calculate that. If you draw a line, you calculate the space or distance between that line and each of these data points. And if it is this, and then you add that all up, an absolute value, add it all up, and you want it to be the smallest number possible. It's called the least squares, the least smallest or the least amount of distance between that line. And that determines your slope and your intercept, because that regression line is going to cross the 0 point, and it's going to determine how steep your actual line is going to be. All right. All right, in this particular case, I'm giving you an example, and this, let's assume this is the 0 line. We've got an intercept of 4.31. Now, what does that mean? Our intercept, remember, it's where it crosses the 0 line on the horizontal axis. If it crosses the 0 line on the horizontal axis, it's not necessarily at 0 on the vertical axis. It's the value of the vertical axis when the line crosses the 0 point. That is your intercept. That is your starting point. So you put a little dot right there. That's where we start. Your slope is 0.41, which means for every unit that you move over, you go up 0.41 on the vertical axis. So we move over 1 unit, we go up 0.41 on the vertical axis. We move over 1 unit, another 0.41. You can see how each time we move over and we go up 0.41, we are determining the steepness or the slope of the regression line, right? Now, there was a process that helped create this regression line, and that was a mathematical process. It was like least squares, which is essentially how we determine where this line should be. And there's only one place where that line is going to be. There's only one place where it's going to be as low as possible when you consider every single data point, or it's going to be as close as possible to every data point in the graph. And that's the way that that's done. Another example, a long time ago, a scientist named Dolbear found that when crickets chirp and the temperature changes, the amount of chirps change as well. So he found that when the temperature goes up, crickets chirp more. So is this a fixed and predictable amount? Well, it was pretty close. We can actually use cricket chirps as a thermometer to determine how warm it is outside. It's pretty close, but it has errors. All models have errors, and we'll talk about error quite a bit in a bit. Well, actually, we'll talk about error now. Okay, so we'll use Dolbear's cricket chirps. So we have an input of x, the number of times a cricket chirps in a minute. And we use that, record that. That becomes our old data. We accumulate enough of it that we can then plot it and create a slope and intercept. Place a regression line and find out what the slope and intercept are for that particular model. That will lead us to predicted y values for each x. But we also have, in our training data, we also have the actual value. We know what the real y value is, but the model gives us a predicted y value. So I'm using z as a kind of the reality. This is what we really know. We know that, the cricket chirps 60 times and it's 70 degrees outside, but our model said it was going to be 72. So the model is close, but it's not quite exact. So we need to take note of the fact that there is error built into our model. Each time that we take an input variable and we predict an output variable, we know that there's going to be some amount that's going to be off. Ideally, we want it to be off as little as possible. And it's only in examining the predictions made on the training data set, where we have the actual values, the actual output values, that we can determine how accurate our model is. So we will look at that model, we will look at that, and we will take into account in the training data how much error is there. The actual formula for calculating the output y's, the predicted y's, is going to be to take x times my slope plus my intercept and also account for error, because I want to be able to adjust this value in order to be able to make it as accurate as possible. The best models will have the lowest errors, and the regression line is determined using the lowest cumulative error. So remember when I said we want to put a regression line on the data that is as close as possible to every line or every point in the plot? That is done by looking at the distance of each data point from the regression line and minimizing that value. So it's the same thing that we're doing here. We're trying to make the model as correct as possible. The quality of the prediction is dependent on the size of the error, and error is a factor of the quality and size of the initial data set. If we have a lot of variability in our data set and we don't have a lot of relationship between our variables, we are likely to have more error, and that can really compromise the value of what we wind up with. So in short, the error is how far off each of our predictions was. We can look at it individually by data point by data point, or we can look at it in aggregate. We can take all of the errors, we can square them, we can add them up, and we can take the square root, and that will give us a measure of the overall error in the data set. Here are some more visuals. We have our regression line. This is back to the flower example. We have our regression line. We know what our intercept is. We know what our slope is. And now we're looking at specific data points. Now, if you look at this particular data point, I think I put my arrow on top of the data point, so it's kind of hard to see. You see that the error is larger because it's farther from the regression line. If you look here, you would see that it's a little bit closer to the regression line. So it's more kind of close, spot on. So each time we look at a measurement, we can see what its error is. And then in aggregate, we can add all of these up, take the absolute values, add them all up, and determine how much error there is in this regression model. And this is kind of a way to do that. We would calculate the sum of errors for all the data points. So we take each individual measurement. This is the predicted value. This is what we actually had. This is, of course, coming from the training data set where we have both once we've run the model. We see that we have 0.2, negative 0.3, 0, negative 0.9, and 2. If we add all these up, they're probably much going to turn around to be something really close to 0 because they cancel each other out because there's negatives and positives. So what we do is we square them all. So 0.2 gets squared, negative 3 gets squared, 0 gets squared, negative 0.9 gets squared. They all get squared. And what happens to the negatives when they get squared? The negatives go away. So then we take the values. They're all squared values. We add them up, and we take the square root, and that becomes the standard error in our model. So how do we know if our model, we've created our model, we've done the slope, well, we've got the slope, we've got the intercept, we have our predicted values, x, we looked at the relationship to the actual values, y, and we built a model, and now we want to look to see if our model is any good. Okay. Well, there are two things we can look at. One of them is r squared, and the other one is f. And until I show you this in a graph, you're not going to know what it means, but I'll go through them anyway. R squared is the amount of variation that our model was able to account for. When you think about building a regression model, you're trying to predict what an output is going to be based on an input. But if our data is really not good at all, if our data is not clean, if we don't see a real good relationship, sometimes we're not going to get a very good model. It's not going to be accurate. It's going to be highly error prone. And sometimes it could be just as easy just to say, okay, well, instead of using this model, just take the average and use the average. Use the average as my predictor. So let's go back to our used car example. The used car example, let's say we don't have a model. We can't build a model for whatever reason. So instead of coming up with a model-derived price for the 100 cars, for each of the 100 cars that we just got the shipment on, we're just going to go back into the database and we're going to calculate the average price that we sold all those cars for the last 3 years, and we're just going to use that average. Now, that's really not a good solution. It's not a good solution because we want it to be better informed. We don't want to leave money on the table. We don't want to try charging too much for certain cars, and using the average is really just not a good way to go. What R squared tells us how much of the variability we are able to account for in our model. So if our model is really good, our R squared is going to be very good. It's going to be very high, and R squared is a correlation coefficient, so it's going to run anywhere from 0 to 1. So if we get an R squared that is like 0.8, 0.9, it means that the variable, the independent variable, was able to account for the variation in the dependent variable at a very high rate. And so we have a really good model. We're dealing with a very strong way of being able to predict prices. The other one is F, and that is an F statistic. And what the F statistic does is it tells us how much better our model is than if we were to have used the average. So how much did we gain by using a regression model over just taking the average of the car prices for the last 3 years and using that value? So that's what those two things are for, R squared and F. R squared tells us about the relationships and the amount of variability we were able to account for, and F tells us how much better we are off with then using the mean. And here's a little bit more on the F statistic. The F statistic is a measure of how much better our model is than no model at all. So if we just had a horizontal line, we would have no model. That would be basically a mean value across a data set. We get a lot of error because it would be pretty far from most of the data points. They would probably be a lot higher and a lot lower. And the total error would be the distance that from the horizontal line to each of the points for each of the data points. So, but when we have a regression line, we have a model, and hopefully we get less error. It's fit to the data, so it fits better. Total error is the distance from the regression line to each data point, as we've seen, but that's going to be a lot smaller than if we just use the mean line. The F statistic tells us how much better off we are than just using the mean. And here's a visual. If you look at this is X is body mass index and Y is total cholesterol. And these are some measurements that we have. Looks like it would be a good fit for a regression line. Looks like it has an intercept here of about 158, I'm going to guess right around there. And then we can calculate the software will calculate the slope for us, calculate the intercept for us too. But if we didn't use the regression line, we would have to basically take the mean and say the mean is right here. I don't know if that would really actually be the mean, but say the mean is right here, about 210, 215. Look at the distance of some of these data points from that line. So we know that this is not a great way to go. This is not a great way for us to be able to predict one variable, total cholesterol, out of body mass index. We're not going to get something that's very accurate. There's going to be way too much error. If we use a regression line, we're going to be much closer. This is going to be the line, of course, that was placed so that it is as close as possible to all data points, the one singular value, and when we use that to predict the values, when we have a body mass index, we can predict total cholesterol. And you can see that the F statistic tells us just how much better off we are by having a regression model than by using the mean. If your F statistic in any model turns out to be fairly low, it's probably an artifact of the data being too varied or the data being not very reliable. Okay, we also want to know about significance. Okay, we've talked about significance in p-values, and I'm not going to go through a lot of this. When I first wrote this presentation, we hadn't really covered p-values, but we've covered p-values a lot so far in this course. So basically, the significance is how significant is our measurements, right? And we will get a significant measurement on the F statistic, just like we did in ANOVA. We will get it in regression as well. And in fact, we do get an ANOVA in the regression results. It tells us how much better our groups are. So that's all you need to know because you already know about everything you need to know about p-values anyway. Okay, so to recap, the things we want to get out of regression. we will get the slope. That is the rate of increase or decrease in the vertical in y when x changes by 1 unit. The intercept is the starting point, or the place where the regression line crosses the vertical axis. It's our starting point. And then we add on to it or decrease from it depending on the shape of the slope, the regression line. The r-squared value should be somewhere greater than 0.7 for the model to be really useful. We want it to be as high as possible because what it's telling us is how much the independent variable is accounting for, how much variability the independent variable is accounting for in the dependent variable. The f value should be greater than 1, hopefully more, for the results to be meaningful, but that's just showing us how much better off we are than if we had no model at all. It's the simplest way of looking at it. And then the significance, or the p-value, should be very low, usually lower than 0.05, and that applies to the F statistic. So here's an example. I pulled this out of Excel, and this is an example of the kind of results you're likely to see when you build a model. Okay, and it doesn't like build the model; it just shows you what you need to put in your model. Okay, so when we look at the regression statistics, we wanted to look at r-squared. R-squared, remember, is the amount that the independent variable, the amount of variability that the independent variable was able to account for in the dependent variable. And in this model, that is 0.44, so about 44%. Not great, not terrible, but not great. Still probably useful, and still probably quite a bit better than if we didn't have a model at all. If we have multiple variables, and you can have multiple independent or input variables that are predicting your output, then we would look at the adjusted r-square, because the adjusted r-square is going to be different because it's going to take into account the fact that you have more than one input variable. So, but for now, we're doing simple linear regression with only one input variable, so we'll look at r-squared. Under the ANOVA, it's giving us the measure, and you're familiar with some of these values from the work we just did in the last module on ANOVA. You're going to look at this. And what ANOVA is really telling us here is it's telling us how much better off we are than if we had no model at all, right? If we had to use just the mean, the ANOVA is essentially saying, well, you're a lot better off using this model than if you didn't use the model at all, because our F value, our F statistic is 31.94, and our significance is very low. So that's good data, and we want to use that. But what we really use to build the model are the values below. You see that you have the intercept. The intercept, remember, is the 0 point on your regression line. It's where your regression line crosses the vertical axis. And in this particular example, which this is the Christmas sales example, in this particular example, we are starting at $30.48, and we build from there. And how we build from there is for every dollar that was spent from January 1st to November 31st, we multiply that amount of dollars by the sales slope. Okay, that's your slope. So for every unit of increase, we multiply it by that amount. Okay? And that will get us increasingly large amounts. And you say, well, wait a minute, you're multiplying that by a value less than 1. So it's actually going to decrease. Well, that makes sense, because imagine somebody comes in for 11 months and they spend a whole boatload of money. They're probably not going to spend that boatload of money in December. They might spend a lot of money in December, but not going to spend nearly what they spent for the other 11 months. So we are only taking a portion of every dollar that they spent from January 1st to November 30th to determine what they would spend in December. Okay. The other values are here. We can look at them. You can read statistics books to find out what they are, and if you're interested. But for now, just look at these 5 things. What is your r-squared? What is your f? What is the significance of f? What is your intercept? And what is your slope, or what is your sales value? And you'll notice that it doesn't say slope. It says sales. This is the variable that was used to derive this value. So this is your input, your independent input that was used to derive this value. Here it is visually. So we have a relationship between our November to January and our December. Okay, and we've got a slope. We've got an intercept, 30.49. Look at that. A 30.49 would be right around where it crosses the vertical axis. That is our starting point. The line doesn't extend to the vertical axis, and I wish it did, but in this particular graphic it doesn't. But it's 30.49. Great. Then we have an r-squared of 0.44, which I'm not really terribly thrilled with, because there's a little bit of scatter in the data, and that's what's explaining the lower r-squared. because it's not just tight packed around that line. It's got some variability there. Our F value is 31.94, which means we are a heck of a lot better off than if we just use the mean. I mean, look at the distance of some of these data points from the mean. We would have so much error in that model, so we're much better off. And our significance is very low. As you saw, our p-value for that's letting us know how confident we are, and the F value is very low. So this is a useful model. So what are we going to do with it? How do we do anything with this information? Well, now we build our model. Okay? Remember that X is our annual sales. That's from January 1st to November 30th. And Y is our Christmas sales, our sales at Christmas time. So we will use the amount that a dollar bought from January 1st to November 30th to predict how much they will buy, or that a customer bought, I should say, just to predict how much they'll buy in December. And this is how we do it. It's based on the general linear model. Our Y is equal to our slope times the input variable plus the intercept. And oftentimes they'll put the intercept first, so it'll be intercept plus slope times X. They've tacked on plus error over residual. We'll worry about error later, but remember every model has error, and so we want to consider error at some point, probably after we've looked at the existing data and seen how far off we are from our actuals, how far off our predicted is from the actuals. Then we can consider error, and that will give us a measure of how accurate our model is. Here is our model. We said that predicted Y, oftentimes the Y for a predicted Y has a little hat on it, which is a little kind of arrow at the top. If you look at your keyboard, it is above the 6. And so that is an indicator that is at a predicted value. Okay? So our predicted Y, in this particular case, is going to be our slope. Our slope is 0.19. Times whatever our input value was. If they spent $100, if they spent $250, if they spent $1,000, that's what goes in there. And then we do this for every single customer, right? And then we're going to add in our intercept. Our intercept is the point where we start. It's the point where we cross the vertical axis. And that is going to give us our predicted value. These two values are derived by the statistical software. As you saw, we pulled them right out of the results, and we are able now to plug in our x's. So if x equals $100, then our predicted Y, should have a little hat on it, equals the slope times 100 plus the intercept, or we can expect the customer to spend $49.66 in the month of December. But if X equals 250, we do the same thing, except we just swap out the 100 for 250. So our predicted Y is going to be equal to our slope times the 250 plus the intercept, or we can expect the customer to spend $78.42. Okay. So these are predicted values. And if we're looking at our training data, they may be different from the actual values, and that difference is the error. And we'll want the error to be as small as possible. So what do we do with this information? Now that we have our model, we can use it to make predictions for what we don't know. So when we get to the end of November, possibly, and this is kind of a fictitious model because it doesn't give us a lot of time. We might want to do this towards the end of October so we can use November to market to these customers. But anyway, that's neither here nor there. We can predict future yearly sales and have them predict the Christmas sales. We can use it each year to know who we should market to, or who we should not be sending marketing information to because they didn't spend a lot of money, or it's just not likely to be worth our time. Or we might even create like a gold customer category because we know that they've spent a lot and they're likely to spend a lot in December. But it allows us to make actionable decisions about how we deal with our customers because we are able to use old data to predict what's likely to happen in the new data. So I'm going to create a separate video because this one's really long already. But I'm going to create a separate video where we go through this in JASP. We're going to use a data set that has anxiety, exam scores, and the amount of hours spent studying. And we're going to see if we can use the amount of hours spent studying to predict the exam score at the end of the exam. Okay, so look out for that video. Hopefully you'll watch this one first and you'll watch that one second.